Okay, we will discuss one more very important problem which is based on the stress concentration. Now we will understand the given problem. Okay, a flat plate subjected to a tensile force of 5 kilonewton as shown in figure. Okay, a flat plate is subjected to a tensile force of 5 kilonewton as shown in figure. The plate material is a grey cast iron. Okay, the plate material is a grey cast iron having sigma u, the ultimate stresses of 200 MPa. Okay, the ultimate stresses of 200 MPa. Here we need to determine the thickness of the plate. Okay, we need to determine the thickness of the plate called H. Okay, here what we need to find out? We need to find out the value for H. So H is equal to, we don't know. H is equal to question mark. Okay, we need to find out. So apart from that, okay, we need to find out that stress concentration, and finally we need to find out the thickness of this given problem. Okay, the value called H or T. Okay, H or T. Okay, this is the thickness of the given plate. For that, okay, here we have the general considerations called K sigma. We all know that. Okay, sigma max divided by sigma nominal for axial load. Okay, where sigma nominal is equal to F by A. We know that. Okay, nominal stresses with respect to axial load, that is a F by A. Okay, where for example if it is a plate, okay, area is equal to, what is the equation to find area? H into D. Okay, H into D. Then we need to find out the maximum stresses, sigma maximum. How we can find out? Ultimate stress divided by N. Okay, which is how the factor of safety. We need to consider the factor of safety of 2. Okay, the factor of safety of 2. Okay, then we need to find out the thickness, okay, with respect to this direct load. Okay, so this is a given problem. This is a given problem. Okay, now first note down the given data. Note down the given data. What is the value called F is equal to a tensile load or tensile force of 5 kilonewton. Okay, that is equal to 5 into 10 to the power 3 Newton, and sigma u is equal to 200 MPa, and the factor of safety N is equal to, the factor of safety N they have given the problem, that is 2.5. Okay, 2.5. Okay, here we need to find out that maximum allowable stresses, maximum allowable stress, that is sigma max is equal to, what is the equation? Sigma max is equal to ultimate stress divided by factor of safety. Okay, so this is with respect to given stresses. Okay, either it should be an yield stress or ultimate stress, okay, which is given in the problem. Here we have ultimate stresses, okay, with respect to this grey cast iron. For that I'll consider sigma max is equal to ultimate stress, okay, divided by factor of safety. If you substitute that value, okay, we know that what is the ultimate stresses? 200 divided by, what is the factor of safety? 2.5. We will get 80 Newton per mm square. Okay, we will get 80 Newton per mm square. Okay, this is the maximum allowable stresses. Okay, maximum allowable stresses. Okay, here we have two cases. Okay, here we have two cases. Okay, so we need to consider here very important. Okay, two cases. One case is across the hole. Okay, case one is across the hole, or okay, the case 2 is okay across the fillet. Okay, so here we have two two cases. Consider two suctions. Consider two suctions. Okay, consider two suctions. two sections, one across the hole, one across the hole, and another one across the fillet. Okay, one across the hole and another one is the across the fillet. Okay, this is the problem. Okay, given problem. Okay, for that here now. Okay, now consider first case. Consider section across the fillet. Consider section across the fillet. Okay, for that this is the given figure. Okay, which is subjected to an axial force or tensile force. Okay, this is the capital D and this is the fillet R and this is a small d, okay, which is subjected to an axial force. Okay, this is what we need to consider across the fillet. For this, what we need to do, okay, we need to find out the d by d. Okay, where capital D is equal to how much? Okay, which is given in the problem. Okay, so this is the capital D is equal to 45, small d is equal to 30, and we know the value for R. Okay, we know the value for R. Okay, if you substitute all these things, okay, capital D is equal to 45, capital D is equal to 45, okay, small d is equal to 30, R is equal to 5 mm. Okay, so R is equal to 5 mm. Okay, so which is figure number 4.24. Okay, from the design data handbook I will show you how to consider that. Okay, figure number 4.24, refer figure number 4.24 from design data handbook. Okay, you can see here this is the case. Here what we need to find out, here we need to find out the thickness. Okay, you can see here. Okay, this is a given problem. Okay, you can see here what we need to find out. We need to find out the k sigma. Okay, in x axis what we have, r by d. In y axis we have k sigma. Okay, so with respect to this we need to find out the k sigma by using r by d as well as capital D by d. Okay, so now we need to find out the ratio. Okay, we need to find out the ratio where capital D by d is equal to, what is the capital D, which is 45 mm, 45 divided by small d 30. If you simplify this, you will get 1.5. What is the r by d? R by d is equal to, where r is the 5 mm, capital D, small d is equal to 30 mm. If you simplify this, we will get 0.16. Okay, so from figure number 4.24, okay, from figure number 4.24 from the design data handbook, okay, in x axis we have r by d, y axis we have k sigma. Okay, here we have capital D by d, okay. So with respect to, okay, the fillet, consider section across the fillet. Now you see here, okay, now you see here what is the r by d, okay, which is given in the x axis is 0.16. okay, what is the capital D by d, which is 1.5. now you see here, this is the, in x axis we have r by d line, in y axis we have k sigma. Okay, here we have, okay, d by d. How much we get? D by d is equal to 1.5. okay, d by d is equal to 1.5. now carefully observe this graph. Okay, so here 0.16, okay, 0.10, 0.15, 0.16, somewhere here we will get. Okay, somewhere here we will get. You draw one straight line. Okay, you draw one straight line which is exactly coincide to 1.5 line. Okay, this is the 1.5 line. okay, where exactly which is coincide, okay, 1.5. And now you draw one more straight line which is parallel to this r by d, okay, you see here exactly which is coincide here, which is the k sigma is 1.8. K sigma is 1.8. okay, this is how you can measure the K sigma, theoretical stress concentration factor, with respect to R by D ratio as well as D by D ratio. With respect to R by D ratio as well as D by D ratio, with respect to this, okay, fillet, okay, with respect to this, the cross section, okay, with respect to fillet. This is how we can find out the stress concentration, okay. Now you can see here somewhere we will get here which is 0.16, we will draw one line, you get 0.16, we will draw one line and you just draw one more line exactly parallel to here, we will get okay, 1.8, okay, that is K sigma is equal to 1.8, K sigma is equal to 1.8, K sigma is equal to 1.8, okay. This is from figure number 4.24, okay, from figure number 4.24, okay, from the design data handbook, okay. This is a value for K sigma, okay. Same way you can find out, okay, the value, you can find out the maximum stresses, okay, by using this one called K stress concentration. Then we can find out the thickness with respect to this, okay, the cross considered section across the fillet, okay. You can see here K sigma is equal to sigma max divided by nominal stresses, okay. So here we know that 1.8 is the K sigma, okay. Then what is the maximum stresses? We will find out in this problem, okay. You can see this is the maximum stresses, maximum allowable stresses, sigma max is equal to ultimate stress divided by factor of safety, okay. Then substitute that value, 80 divided by sigma nominal, we do not know, okay. If we find out that sigma nominal is equal to 44.4 Newton per mm square, 44.4 Newton per mm square, Newton per mm square, okay. Same way, okay, this is a formula, okay. Here we have, then, okay, what is the nominal stresses with respect to axial load? Sigma nominal is equal to F by A, okay, sigma nominal is equal to F by A, okay, where sigma nominal is equal to 44.14, okay. If you substitute all the values into this equation, 4.4 is equal to, what is the F, okay, the tensile force which is acting on this particular plate is 5 kilonewton, okay, 5 kilonewton, 5 into 10 to the power 3, 5 into 10 to the power 3 divided by, what is the value for H, where A is equal to H into D, area, okay, A is equal to H into D, where A is equal to H into D, H into D, A is equal to H into D, okay. If you substitute that value, H into 30, H into 30, H is equal to 3.75 mm, okay. If you simplify this, you will get this value. If you simplify this, we will get this value. H is equal to 3.75 mm, the plate thickness, okay. Next we have one more very important section, okay. Here what we need to do, we need to consider, okay, we need to consider section across the, consider section across the hole. Here we have, okay, this is a figure we have, consider the section across the hole, okay. For that we need to consider figure like this, need to consider figure like this. Here what is the diameter? It should be 30, the plate thickness, okay. Here we have the diameter of the hole which is 15 mm, okay, which is also subjected to an axial force, okay. This is a second case what we have, okay. Here width width of the plate is 30 mm, okay, and diameter of the hole D is equal to 15 mm, okay. And here what we need to find out, instead of R by D as well as D by D, okay, here what we need to find out, okay, so D by W ratio, okay, D by W ratio, okay. So here we know that W is equal to, D is equal to 15 mm, W is equal to 30 mm. If you simplify this, we will get 0.5, okay, 0.5. From now, from figure number 4.5, okay, figure number 4.5, refer design data handbook, okay, for D by W, okay, D by W ratio of 0.5, okay. Now you see here, okay, I will show you how to take the value for figure number 4.5 in the design data handbook. In the design data handbook, I will show you that how to take that value from the design data handbook, okay, with respect to D by W ratio. You see here, okay, this is a formula, this is a table we have, okay, this is a graph we have, K sigma maximum with nominal, okay, you can see D by W, this is a, okay, cross section by considering hole, okay, you can see W we have and diameter of the hole we have, the plate is subjected to an axial force. You see this is a D by W, okay, how much we will get D by W? D by W is 0.5, you see this is a 0.5, okay, so you just see 0.5 where exactly it is coincide around, okay, which is exactly coincide exactly, okay, just below that 2.2 line, just below the 2.2 line, which is, okay, I will consider that value as a K sigma, okay, the K sigma, you just see the nature of the graph, okay, this is D by W of 0.5, okay, 0.5, here we have, okay, 2.2, 2.4, that is K sigma, okay, K sigma, where somewhere exactly which is coincide here 0.5, exactly draw one line, okay, which is K sigma is equal to 2.18, K sigma is equal to 2.18, this is the value, for the stress concentration, okay. Same way we need to determine the thickness by using these values, okay. Here K sigma is equal to sigma max divided by sigma nominal, okay, that is equal to 2.18, that is equal to 80 divided by sigma nominal, okay. If you simplify this, sigma nominal is equal to 36.7 Newton per mm square, 36.7 Newton per mm square, okay. So we know that, okay, nominal stresses with respect to axial load, sigma nominal is equal to, what is the formula? F by A, okay, F by A. How to find out that area, okay, with respect to a plate with a hole, okay, we already discussed one problem in the beginning of the classes itself, okay, you just observe here, okay. So here area is equal to width minus D into H, okay, width minus D into H. If you substitute this value into this formula, okay, we know that axial force of 5 into 10 to the power 3 divided by, okay, width, okay, 30 minus 15, okay, 15 is nothing but a diameter of the hole and we don't know the H is in the sense thickness of the plate, If you simplify this, we know the sigma nominal, that is 36.7, okay. If you simplify this, H is equal to, okay, 9.08 mm, okay. So always what we need to do, okay, we need to adapt, okay, always we need to adapt the larger adapt the larger value of this one, adapt the larger value of 9.08 mm for 9.08 mm for better design. For better design. Okay, so this is a given problem. Okay, this is the given problem. Okay, so here what we need to find out, we need to find out the thickness of the plate. Okay, thickness of the plate which is subjected to a tensile force of 5 kilonewton. Okay, 5 kilonewton. Thank you.